For 4.1, and as we start in on this unit, you have to make sure that you have a scientific calculator to complete any of this work. If you don't already have one, I would encourage you to purchase one or borrow one. One that I use is just this TI-30 here. Things that you need to make sure you have is like an LN button, because the simple calculators will not be able to execute this unit 4 stuff. So with this section, what we're going to do is we're going to go into exponential functions. When we're working with exponential functions, you'll notice that now the variable is in the exponent. We've worked with a lot of functions up until this point, but we have not worked with any where the x was in the exponent. We've only looked at different powers of x and different things with that. So with this, we're looking at, this is considered our base, so it's just a base a. It could be any number, where x is any real number, and a is greater than 0, so it's positive, and a cannot be equal to 1. So to kind of get our feet wet and get us going with these exponential functions, I just want to kind of work around with two of them and kind of notice how they look, what's going on with them, and then we're going to kind of put some characteristics together. So let's look at this first function here, and we're going to kind of go slowly through the first one, and the second one will go a little bit quicker. So you'll notice I have the function f of x equal to 2x. Well, what I want to do is I want to plot some points and then come over here and graph it so we can see what the shape of this function looks like, because we've looked at a lot of parent functions like we did in Unit 1, but we have not looked at anything with a variable in the exponent like this. Okay, so I want to plug in, these are my x values, so I'm going to plug in right here for x this -3. So I'm saying, okay, that's 2 to the -3. If you remember basics of working with exponents, when you have a negative in the exponent, you can put this over 1 and move it to the bottom, which gives you 1 over 2 cubed, which is 1 over 8. So when I plug in -3 for that exponent, I get 1/8. Let's do it again, plug in -2. So I have 2 to the -2. Again, to get rid of that negative exponent, I can put this over 1 and move it to the bottom. So it gives me 1 over 2 squared, which is equal to 1/4. And then I have 2 to the -1. Now, I do want to show you in your calculator how to do that. I wanted to do 2 of them just with the basics of exponents so you can understand how the 1/8 and the 1/4 came to be. But let's look at this 2 to the -1. If I want to raise 2 or anything to a different power other than just squared, on my calculator here, you've probably been using the squared button here. You'll notice I'm going to do 2, and then I kind of have this house top button here, and your calculator may be different. So either pull out, like in my case, it comes with this little card that will help you to find how to do your functions, or look on there for similar buttons. So I'm going to raise it to the parentheses -1, and I'm going to close parentheses. I always want to keep in parentheses what I'm raising this to so it doesn't accidentally only do a piece of it, and you'll see later in this lesson why that's important. So that gives me 0.5, which is equal to 1/2. You can go on, you can say 2 to the 0. Well, anything to the 0 power is 1. 2 to the first, that's 2. 2 squared is 4. And 2 cubed is 8. So now that I have some function values, let's go over to our graph and see if we can graph them. So at -3, 1, 2, 3, we're going to be at 1/8. I'm just going to estimate. At -2, we're at about a fourth. At -1, we're at a half, getting better here. At 0, we're at 1. At 1, we're at 2. At 2, we're at 4. And at 3, we're at 5, 6, 7, 8. So you can see this graph starts down here and slow. It was slow at first, but then it jumps up dramatically here. So some key things I want you to know about this graph, or looking at this, we can see that all of our f of x are positive. So you can see that even when I was plugging in negatives, it just gave me fractions. I never got any negative values in these y values. Another thing that you'll notice is, as x increases, f of x increases. So as our x's are getting bigger, our f of x's were getting bigger, but they were increasing faster. And the last observation I want to make about this is, as x decreases, f of x decreases, and approaches 0. So you can see as your x's are getting smaller, your f of x's are getting smaller, but they're approaching 0, and we never actually drop below this x-axis. Okay, so we got our feet a little wet with that one. Let's do this next one. I'm going to do the similar approach here. So now we're plugging into 2 to the negative x. So I just want to see what happens when we have that negative right there. So I'm going to say, okay, that's 2 to the negative from the formula, negative 3 from the x. Well, that's just 2 cubed, so it's 8. And then 2 to the negative, negative 2, again, negative from the formula, negative from the x, so that gives me 2 squared, which is 4. 2 to the negative, negative 1, that's 2 to the first, so just 2. 2 to the negative 0, well, that's just 2 to 0, so 1, because anything to 0 power is 1. Let's see, 2 to the negative 1, well, that's like what we did up here. 2 to the negative 1 is 1/2. 2 to the negative 2, again, we saw 2 to the negative 2, you can move it to the bottom, which gives you 1 over 2 squared, which is 1/4. And then 2 to the negative 3, that would be like 1 over 2 cubed, so 1/8. Okay? So you can see just putting in that negative there just kind of reverse the values I'm looking at here. So when I go over and graph it, at negative 3, I'm going to be at 8. At negative 2, I'm going to be at 4. Negative 1, I'm at 2. At 0, I was at 1. Then a half, then a fourth, and then an eighth. So you can see from this graph, similar structure, all of it's in those top 2 quadrants. But let's make some notations about what we see with this one. First of all, we see that 1, all the f of x are positive. 2, we see that as x increases, f of x is decreasing, and it's approaching 0. So as our x's were increasing, f of x was decreasing, it was getting closer and closer to 0. And then as x decreases, f of x is increasing faster. So just some observations I wanted to note about this graph, but I do want to kind of put all this together and make some assumptions about our exponentials just in general. So let's kind of fill in this table here and think about what's going on with these exponential functions. First of all, our domain. Remember, domain is all your possible x values. Well, we worked with negatives, we worked with zeros, we worked with positives, and so the domain for both of these was all real numbers. Our range, that's our possible y values. You notice from the graph that the y values were restricted in those upper quadrants. And so they went from 0 to infinity on both of them. So you can get really, really close to 0, but it'll never include 0, so we want to put our parentheses right there on the 0. Our y-intercepts were both at 0, 1. So that's interesting. And then we saw when we had something just raised to the x, that was an increasing function. It was increasing the entire way. And then when we put the negative up there, it was a decreasing function. And the type of function, both of these were actually one-to-one functions. None of the x's repeated, none of the y's repeated. So this is great to see that exponentials are one-to-one, because it means that, going back to what we were doing with inverses, that we can get an inverse function of this, and that's going to be beneficial as we move forward. So adding on to what we already know, we've already learned about transformations in other sections with all of our parent functions and how we can move those around. So let's see how that benefits us here with our exponentials. So just kind of discovering all the ins and outs of an exponential and getting all the characteristics and transformations, etc., like we did on the other one. So remember, when you're adding a number on the outside of the function, this is going to move your function up and down. Remember, if it's positive, it's going to go up. If it's negative, it's going to go down. And so like if we had f of x equal to 2 to the x plus 1, that plus 1 right there would move our whole function up 1 unit. Then also we learned that if we have plus or minus on the inside, remember that is going to move you left and right. It was the opposite of what you think. So positive was going to move you left and negative was going to move you right. So therefore f of x is equal to 2 to the x plus 1. And that little plus 1 right there would be 1 unit to the left. And so it's still happening inside the function, but we kind of see that it's happening up there in the exponent, which we haven't seen before. With this one, when we have a negative on the inside, this gives us a y-axis reflection. So such as the one we just graphed, 2 to the negative x. And then, let me modify my notes here. If I have negative on the outside of it, this is going to cause an x-axis reflection. And so f of x would be equal to negative 2 to the x. That would be an example of that. So as we continue our discussion with these exponentials, there's one exponential that's really special, and we're going to work with it a whole lot in this unit. It's called the natural base e. Now the natural base e is a button that you will find on your calculator. So I'm going to show you my calculator quite a bit today. You'll notice that wherever your LN button is, there is typically where your e to the x button is. You can see mine's kind of in gray, so I'm going to have to use this button to access it. And so when I hit second LN, my e is going to come up and I'm going to have to raise it to some power. If I just do it to the power of 1, you can see it's this decimal number here that I have written out. So this E button is similar to your pi button in the fact that it is a value, it is not a variable. And then here's a nice graph of it as well, and you can see it follows suit to what we were just doing with the last function. So I wanted to talk about this natural base E button and show you where it is, but now let's kind of work with all of our buttons and talk about how we can plug in just straight evaluations of these exponential functions. So I've got 3 little practice problems for us here. It says let f of x equal 5 times 3 to the x plus 1. Evaluate f of 2 without using a calculator. Okay, so I'm going to say 5 times 3 to the 2 plus 1. Now remember order of operation. Order of operation says that you do parentheses, then your exponents, then you multiply and divide, and then add and subtract. So you have to address your exponents first in doing this. We will not multiply 5 times 3 first. We will address the exponent. So that's 5 times 3 to the 2 plus 1, which is 3. So first you want to do the exponent. 3 cubed would be 3 times 3 times 3 is 27. So then 5 times 27 would give me 135. So I want to emphasize here order of operation because those are some of the most common mistakes that I see in a student evaluating an exponential. You try to multiply the 5 and 3 together first, and 5 times 3 is 15, and 15 to the third power is not 135. I've had a student say before, my calculator is doing it wrong. No, your calculator is doing whatever you tell it to do, and it always follows the order of operations. So if you're not inputting it correctly, you will have issues. Now this one says using a calculator and round to 4 decimal places. So this would be 8 times 1.2, let's see, x minus 5, so it would be 3 minus 5. I always try to do as much arithmetic as I can before I run to my calculator. 3 minus 5 is negative 2. So that when I go to my calculator and I go to type this in, I'm going to say 8 parentheses 1.2, and then I'm going to raise that to the negative 2. So my order of operation is going to do my exponent first, or even likewise if you want to do 1.2 raised to the negative 2, and just do this, get your exponent. So it gives me an answer. Now I'm not going to write that down because I'd have to round it, so I'm just going to leave it in my calculator. When I hit the times button, it takes my previous answer and multiplies it times 8. So I get this answer here. Now it told me to round to 4 decimal places. So let's take a quick moment to remember how to round. So this would be 5.5555. If I want to go to 4 decimal places, I look at the fifth, and if it's 5 or larger, it'll round this one. So it would be 5.5556. I do take off for rounding. Rounding is a concept you should know before entering this course, so make sure you round appropriately. Next, let's play with our E button. Use a calculator to find e to the negative 0.5, round to 5 decimal places. So we're going to have to go in here. Again, your E button, here's your LN button, so it's going to be right there with it. So I'm going to say second E to the negative 0.5, close it, enter. So I get, again, 0.606530. I want to go to 5 decimal places, so 1, 2, 3, 4, 5. So if I look at my sixth one, it's not 5 or bigger, so I just leave it the same. So it'd be 0.0653. So make sure you round appropriately so you're not missing these small points along the way. So now that we kind of are getting our feet wet with exponentials and we can talk about how to enter in them calculator, let's see the application in it and just kind of work with that a little bit. So in part 2, we're going to be looking at exponential growth. An exponential growth or decay function grows or shrinks at a constant percent growth rate, and it may be modeled either with this function here or this function here. Although they look different, all they are doing is making their b into that 1 plus r. And so it just depends on what we're doing with it, on which one we want to use. Now, what do all these letters mean? A is going to be your initial or your starting value, so you can see the A is there. R is your percent growth or decay rate. And B is your growth factor or growth multiplier. So if they give you a growth or decay rate, we're going to go to this one. If they give us a growth factor or a growth multiplier, we're going to go to this one. So let's kind of keep this on the side and let's work some problems and see what we can do with it. So first one says, example, India's population of 1.14 billion in the year 2008 had a percent growth rate of 1.34%. Write an exponential function for India's population and use it to predict the population in 2020. So we need to create an equation and then use our equation. So let's look at what information we have. 1.14 billion in the year of 2008 means that, okay, in 2008, so that's my year, it was at 1.14 billion, so lots of people. And then it says it has a growth rate of 1.347, so I know R is going to be equal to 1.34%. Write an exponential function for India's population and use it to predict the population in 2020. So in 2020, I'm trying to figure out what the population is. As you've seen in earlier units, when we're working with years, we never use 2008 or 2020. We normally have like a base year. So let's call this one t equal to 0. And then when we go from 8 to 20, that would be 12 years later. So we'll call that to be t equal to 12. So when we're working with this problem, we learned that A was our initial value and our initial population starting with 2008 was 1.14 billion. So I'm going to use 1.14 for my R. Now when you're working with your rates, we always want to change them into decimals. So I'm going to move it 2 places to the left. So I'm going to be using 0.134 when I'm working with my calculations. Make sure you also always get it out of that percent. So now let's go over here to our formula from the previous page. F of t is equal to 1a times 1 plus r to the t. And so that gives me, let's plug in what we know. So f of t would be equal to 1.14 times 1 plus 0.034 raised to the t. So there, I have an equation. It says write an exponential function. We did. Now I can clean this up a little bit, and I can actually add those two numbers together. So that would be 1.0134 to the t. Now I need to find out what is the population in 2020. Well, we already decided we're going to use 12 to represent 2020. So I'm going to say 1.14 times 1.134 to the 12th. Now, again, when you go to your calculator, you want to enter this first and do your exponent first. So I'm going to say parentheses 1.0134 raised to the 12th. There's my value. Now I'm going to multiply it by 1.14. So when I'm finding f of 12 is going to be equal to, I did this, times 1.14. That would be 1.34 billion. So we can see in 12 years, they're going to grow from 1.14 billion to 1.34 billion. Although these are small decimals, this is in the billions, so that's quite a bit of growth in population. So I just want to be able to identify these key variables, create my function, and then utilize it to predict what the population was in 2020. Let's do one more example. This one is going to deal with some decay. Bismuth-210 is an isotope that's radioactively decays by about 13% each day. So that's going to be information we need. Meaning 13% of the remaining bismuth-210 transforms into another atom, polynonium 210 in this case, each day. If you begin with 100 milligrams, how much remains after 1 week? So information that we want to grab from this is we want to say, okay, it radioactively decays at about 13%. So since that 13%, that's going to be my R. So if I change that into a decimal, I get 0.13, and it's decay, so we're going to be going down by 13%. I'm beginning with 100 milligrams, so my A is going to be 100. And then it says it's decreasing by 13% each day. How much is it after 1 week? So we need to be in the same unit. So our time is going to be 7 days because that's how it's decreasing by days. So we're going to make, instead of 1 week, we're going to call it 7 days. So if I'm finding f of d, so our function in relation to days, this would be equal to 100, 1 minus the 0.13 because I'm decaying, raised to the d. So this would be equal to 100. 1 minus the 0.13 is 0.87 to the d. So there's my function. Now it wants me to know how much is it after 1 week. So now I'm going to plug in 7 here. So I have 100 times 0.87 to the 7th. I'm going to go to my calculator. And I'm going to say parentheses 0.87 raised to the 7th. Get that number. And then I'm going to multiply it by 100. So this gives me 37.725. And so how much is going to remain after 1 week? We would have this many milligrams left over after 1 week based on its decay. So I hope this helps with the first section of this section.